Hello, let's work on some problems from section 16.7. You will see this section is actually on the harder side because we need to be able to imagine the surface parameterization, and then we need to put density on it or a function on it, and then we also need to see if you put a vector field on it. Okay, now you can review from my lecture notes, lecture videos about some notation, but I hope at this point you realize that notation is important. Okay, notation is important. Okay, let's start with question number 8. We have that double integrals over surface S, where the surface is parameterized by u and v. How do we do this? So I need to first think about this ds, this guy here, this ds, to remind ourselves that is actually equals to the magnitude of r sub u cross r sub v dA. Okay, so this s is in terms of x and y, right? But then if you want to change the domain in terms of uv, we need to multiply by this guy here. Okay, so r sub u equals to 2v, 2u, and then 2u. R sub v equals to 2u, negative 2v, 2v. So the cross product r sub u cross r sub v will be 4uv, 4uv minus negative 4uv. Okay, that's not too bad. And then the second component, negative of 4v squared minus 4u squared. And the last component is negative 4v squared minus 4u squared. Okay, I don't really like the guy in the middle though. But you can factor the 4 out. Okay, so 4 times magnitude, 4 times uv, no, that's, 4 times 2uv, and then if I factor the negative, and then factor the 4 out, I get negative positive u squared minus v squared, and then the last one I get u squared plus v squared. That's, so what is the magnitude then? The magnitude r sub v, that will be 4 times square root of 2uv squared plus u squared minus v squared plus u squared plus v squared squared. That is 4u squared v squared plus u to the 4th minus 2u squared v squared plus v to the 4th plus u to the 4th plus 2u squared v squared plus v to the 4th. Okay, so I still get that 4, of course, at outside. So factoring the 4 out actually makes our life a lot easier, And I also noticed that this guy will cancel, right? That guy will cancel. So we get 2u to the 4th plus 4u squared v squared plus 2v to the 4th. I can factor square root of 2 out, and inside I get u to the 4th plus 2u squared v squared plus v to the 4th which is a complete squared, right? In other words, that is u squared plus v squared being squared under square root, which will give us 4 square root of 2 times the absolute of u squared plus v squared. Well, but u squared plus v squared always non-negative anyway, right? So I can just omit the absolute sign. Okay, that's just the magnitude. Now, how about the integrand? The integrand x squared plus y squared now becomes 2uv squared plus u squared minus v squared being squared, which will give us 4u squared v squared plus u to the fourth minus 2u squared v squared plus v to the fourth. Okay, so u to the fourth plus 2u squared v squared plus v to the fourth, which is actually equals to u squared plus v squared being squared, right? I don't know if that's useful. Anyway, let's put things together. So this will be double integral over s of x squared plus y squared ds. Now it becomes double integral over d. What is that d? That's the d, okay, which is actually a unit circle on UV plane. Unit disk on UV plane. Okay, the integrand is u squared plus v squared being squared times 4 square root of 2 u squared plus v squared dA. That gives us double, 4 radical 2 double integral over d of u squared plus v squared cube dA. Now, based on what it looks like, that's a unit disk. So I will just make it polar. Integral from 0 to 2 pi, integral from 0 to 1, u squared plus v squared becomes r squared, r dr d theta, independent of theta. So I have that 2 pi. Okay, and this is r to the 7th. So when you integrate, it becomes 1/8 r to the 8th. It cancels nicely, so we get 2 square root of 2 pi. Okay, so notice that it seems like I spend more time dealing with the ds, if you think about it, right? I spend more time dealing with this, the ds. Okay, now please be patient when you do this. Okay, we know that will be long. This is question number 8. Imagine what happened later. But please be patient because the setup is important. Once your setup is incorrectly done, basically a plan of things you do after that becomes useless. Okay, so be very patient and show your work so that you can correct yourself in case you write something wrong. Okay, now at this point, actually, I can say, based on my experience, students who usually don't show their work are the one who usually lose the most, because when they make mistakes, they don't even realize they make mistakes because, yeah, they don't show the work. Okay, yeah. So next, number 12, we have double integral over surface S, where the surface is parameterized is given by z equals to function of x and y, and the domain is a rectangle. Oh, the domain is a nice rectangle. 0 to 1, 0 to 1. Okay, so since it is parameterized by x and y, so we can just use the regular parameterization. Z sub x equals to that's x to the power of 1/2. Is it right? And because this is actually 2 over 3 x to the power of 3/2 plus 2/3 y to the power of 3 halves, right? Okay, so if I do the derivative, I get x to the 1 half for respect to x, respect to y, I get y to the power of 1 half. So 1 plus c sub x squared plus c sub y squared, that is 1 plus x plus y. Okay, so the ds later on will be represented by 1 plus x plus y under square root, I'm sorry, under square root. Under square root. Square root of 1 plus x plus y dA. Okay, and then that's the ds. Oh, it's already there. So double integral over surface S of y ds is equals to double integral over d of y square root of 1 plus x plus y dA. Oh, shoot, how to integrate this? Let's see. I suddenly question myself. That's integral from 0 to 1, integral from 0 to 1, y, square root of 1 plus x plus y. Do I do the dy first or dx first? They happen to be the same for x and y, but because I have y outside, I think I want to do respect to x first. Yeah, the domain is a nice domain though, but the integrand is ugly. Okay, let's see. So if my u equals to 1 plus x plus y, then my du will be dx. That one is easy. But how about the boundary? U at 0 will be 1 plus y, and then u at 1 will be 2 plus y. Okay, so the integral from 0 to 1, integral from 1 plus y to 2 plus y of, oh shoot, I don't think I can do it right here. Y becomes what? U minus 1 minus x. I don't like that because I still have the x then. And then this is square root of u. Du dy. No, not supposed to have a x there. Am I missing something? No, it's not doable. So do it another way. Do it another way. So I will make it dy dx instead. Dy dx. So let's erase this for now. So if I do respect to y, that will be this will be 1 plus x, 1 plus 2 plus x. Hey, hold on. I think what I had earlier was correct. No. It should be if it's respect to. So if I solve for y, that will be. Yeah, that's right, huh? That's not good. So, yeah, that's correct. So let me erase this. Make this dy dx. Oh, I'm sorry, I'm so confused now. So that will be 1 plus x, 2 plus x. The y will be u minus 1 minus x. And then square root of u du dx. Now it's better, right? I hope. Let's distribute that. It's u to the power of 3 halves minus u to the power of 1 half minus x u to the power of 1 half du dx. Integrate respect to u, that will be 2/5 u to the power of 5 halves minus 2/3 u to the power of 3 halves minus 2/3 x u to the power of 3 halves. And this is from 1 plus x to 2 plus x dx. Yeah, we will have a lot of chunks to play with here. Bear with me. Let me do this first. And this will be, I will factor the 2/3 u to the power of 3 halves, and I get 1 plus x here. Okay? I hope that helps. And then, so this integral becomes, I really hope I don't mess up. Look at this, I already kind of like give up. Okay, this is integral from 0 to 1, 2/5, and then, you know what, let me use this. So 2 plus x to the power of 5 half minus 1 plus x to the power of 5 half minus 2 over 3, 1 plus x, and then 2 plus x to the power of 3 halves minus 1 plus x to the power of 3 halves dx. You ugly. I don't know how to do this, honestly. I'm kind of like, I want to simplify this. Before I integrate another one. So this will be patient with me. This will be 2/5, 2 plus x to the power of 5 half minus 2/5, 1 plus x to the power of 5 halves minus 2/3, 1 plus x, 2 plus x to the power of 3 halves minus 2/3, 1 plus x to the power of 5 halves dx. Okay, now that way then I can see the common factor, common factor thingy. This guy is by itself, huh? These guys here I can combine with this, and this guy is by itself. So this will be, let me break it up. So this is 2/5, 2 plus x to the power 5 half dx, and then minus 16 minus 16 over 15 integral -1 to 0 to 1 of 1 plus x to the power of 5 halves dx, and then minus 2/3 integral from 0 to 1 of 1 plus x times 2 plus x to the power of 3 halves dx. Times 2 over 7, 2 plus x to the power of 7 halves from 0 to 1. This is 16 over 15, 2 over 7, 1 plus x to the power of 7 half from 0 to 1, minus this one here. I honestly don't know how to integrate. Actually, not that bad. Okay, so 2 over 3 integral from 0 to 1 of 2 plus x to the power of 3 halves dx, and then minus 2 over x, 2/3 integral from 0 to 1 of x 2 plus x to the power of 3 halves dx. Okay, so this is 4 over 35. When x equals to 1, that will be 3 to the 7 half plus, minus 2 to the 7 half minus 32 over 105, 0 to 1. So that will be 2 to the power 7 half minus 1. Minus, and this guy here will be 2/3 times 2/5. Let me just compute it right away. That will be 5 halves. Okay, so 1. So 3 to the power of 5 half minus 2 to the power of 5 half. And then this one here, I work with that later on. Okay, I'm tired. Okay, so this is 4 over 35, 3 cubed, so that's 27 square root of 3 minus 8 square root of 2 minus 32 over 105, 8 square root of 2 minus 1, and then this guy here 4 over 15, 9 square root of 3 minus 2 square root of 2, blah blah blah, and then combine like terms here. Okay, let me stop here. I don't want to get too much into this. I think it has something to do with the way I did my integration. Suppose I go back. Suppose I go back. Integral from 0 to 1, integral from 0 to 1 of y square root of 1 plus x plus y dx dy. That's what I did earlier, huh? So if my du equals to 1 plus x plus y, and then I make, I'm sorry, that's my u. If that's my u, then my du becomes dx, right? So x 1 plus y here, and then 2 plus y here. You know what? This guy, the y is still there. I don't need to change that y. This is u to the power of 1 half du dy. Okay. That's y 2/3 u to the power of 3 halves from 1 plus y to 2 plus y dy. Not any way easier, but integral, I take the 2/3 out, integral from 0 to 1 of y bracket 2 plus y to the power of 3 halves minus 1 plus y to the power of 3 halves dy. Let me split that into two integrals so that the substitution is easier to do. Why this suddenly becomes calculus 2 class? Okay, it's painful, I know. So I will call this W1, that's 2 plus y, and my W2 2 will be 1 plus y. Okay, so dw1 is dy, dw2 also equals to dy. But then what happened with the integration? The limits of the integral, this becomes 2 to 3. The y will be w1 minus 2. And then this is w1 to the power of 3 halves. dw1 minus 2/3 integral from 1 to 2 of w2 minus 1 w2 to the power of 3 half dw2. Let's go on from here. So this is 2/3 integral from 2 to 3 of w1 to the 5 half minus 2w1 to the 3 halves dw1 minus 2/3 integral 1 to 2 of w2 to the power of 3 halves minus w2 to the power of 3 halves. I'm sorry, that's 5 halves, originally 3 halves here. dw2. So this will be 2/3. And then that's 2 over 7 w1 to the power of 7 half minus 4/5 I don't need this 4/5 w1 to the 5 half from 2 to 3 minus 2/3 2 over 7 w2 to the power of 7 half minus 2/5 w2 to the power of 5 half from 1 to 2 u. Okay, so this will be 4 over 21 27 radical 3 minus 8 radical 2 for the first one minus 8 over 15 8 over 15 9 radical 3 minus 2 radical, I'm sorry, 4 radical 2, and then minus 4 over 21 no parentheses anymore, I think. And then 8 radical 2 minus 1 minus 2/5. Oh no, I'm sorry, minus 1. And then plus 4 over 15 4 radical 2 minus 1. Okay, do we get what we have there? This is 35 supposed to be. Do we get what we have there? Honestly, I don't know yet. Yeah. Let's collect the one with radical 3 first. So let me continue here. So this is equal to 4 times 27 over 21, and then minus 8 times 9 over 15 square root of 3. How about square root of 2 plus 4 times 8 negative 8 over 21 plus 8 times 4 over 15 minus 4 times 8 over 21 and then plus 4 times 4 over 15, all with square root of 2. Whew. And then as for the 1, that will be just 4 over 21 minus 4 over 15. I think that's how I will do it. You know, that's how I will do it. Oh, something cancels here. Negative, and then this becomes positive. Yeah, over 21 also, huh? Surprise. So this cancels here. Is it right? I don't expect that though. Hold on. Okay. If I suddenly do a lot of algebra here. So reduce by 3, this is 7. Reduce by 3, this is 9. Reduce by 3, this is 5. Reduce by 3, this is 3. So I get 36 over 7 minus 24 over 5 radical 3 plus 32 plus 16, 48. That's 48 over 15 radical 2. And then plus 4 times 21 times 15. That's 15 minus 21. Something over 35. 180 minus 24, 7. 168. 48 divided by 15, reduced by 3, reduced by 3. And this is negative 6, so this becomes negative 4 times 2 is 8, reduced by 3 is 7, that's 105. I think if, I want to see if this gives me the right answer though. So this is 12, huh? 12 over 35 square root 3. I may very likely do some mistakes, some algebraic mistakes. But let's see. If I go back to this question, I'm sorry, this is very, very distracting. To get the radical, the one with radical 3, I need to deal with this and deal with this. The one from this part here will not give me radical 3 anymore. Will that? Oh yeah, it will, huh? It will. Okay, I deal with that later on. Or should I do that now? Let me do that now. So this is, I just want to match with the radical 3. So 2 over 3. I do substitution, u, so this is 2, this is 3. So that will be w1 minus 2, and then w1 to the power 3 half dx. Still much to do, but let's see. So this is 4 times 27 over 35 radical 3, and then minus 4 times 9 over 15 with radical 3. Yeah, will we get something like that? I don't know, I don't know, I don't know, I don't know, I don't know. Too much, too messy. My bad. I get distracted with this integration instead. But yes, this is the setup. This is the setup. Okay. And then we have two alternatives. Either we integrate this way or we integrate this way. Okay. Apparently seems like alternative number 2 is easier, but it's still not anyway much easier. Oh, hold on. I just realized something. No. These don't cancel. These two are not canceling. These two are not canceling. My bad. In fact, because they're the same sign, huh? So 32, 64 over 21. No, they don't cancel. They don't cancel. Let me move this a little bit. This should be negative 30 to 64 over 21 plus. Yeah, so the LCD is 105. Is it right? So multiply by 5, 320, multiply by 7, 3 to 3, 48 times 7, 6, 5, 20, 3, 3, 6. So there will be 16. So there will be 16 over 105. So this is 16 over 105. Yeah, this thing here I cannot go further, but you see the technique that I will use here. The technique I will use here is very similar to the technique I will use basically here. Very similar to the one I use here. Okay, in fact they look the same right now. Oh, they look the same right now. Okay, yeah, the second method is better. The second method is better. Yeah. Oh, you see, in this case seems like the setup is okay, but we deal with a lot of radicals. That's the simplifying actually takes me so much time, and I don't like it. I'm sorry. I'm sorry. I'm so sorry. Okay, number 18. Double integral x z ds, and S is the boundary of region enclosed by the cylinder. I think I need to sketch this. The cylinder y squared plus c squared equals to 9. So it is parallel to x-axis. Okay, and the planes x equals to 0. That's the so this is the one on yc plane. And x plus y equals to 5. X plus y equals to 5. So it is cut this way. So later on it will be like this. Slanted. Yeah, slanted. Slanted cut. Okay, so how do I do that? So let's say we have three surfaces here then, huh? Surface 1 is the back, the one that looks like this on YC plane, radius 3. Okay, surface 2 is part of the cylinder, the body of the cylinder, but it is cut this way. Not nice. Maybe like this. I hope that's better view. Okay, and then surface 3 is the front. This part here. Okay, surface 2 is the lateral. Oh, okay, seems like we need to do something. I hate this. I really hate this. Okay, so let's see. Let's deal with S1 first. So this basically this double integral over S of x z ds is the same to the sum of three triple integrals of xc ds. Okay, now for S1, you know what, let me do this. Let me move this guy here so that I have more space for this here. Okay, now for S1, that is this y squared plus c squared less than equals to 9, but the x equals to 0. That helps. That helps so much, because then the double integral over S1 xc ds will be double integral over the domain there, but we already have 0. Okay, that will be 0. That's for S1. For S2, it's more challenging. For S2, we need to parameterize this y squared plus c squared equals to 9. So I will parameterize that with r theta x, where depends on x, right? Okay, and then the y is 3 cosine theta, 3 sin theta. Okay, while, hold on, but the x has some boundary. The x has to be actually the x has to be 5 minus y. So 5 minus 3 cosine x from 0. Okay, so how do we do this then? Okay, so r sub x, that's 1, 0, 0. R sub theta will be 0, negative 3 cosine theta, 3 cosine theta. So the cross product is 0, and then negative 3 cosine theta, and then am I right? And then negative 3 sine theta. Okay, so I can factor the negative 3 out. 0 cosine theta sine theta. Okay, but the magnitude therefore is 3, huh? Oh yeah, the radius is 3, right? Okay, now then what happened to the integrals? So double integral over S2 of xc ds will be double integral. The theta will be from 0 to 2 pi. The x will be from 0 to 5 minus 3 cosine theta. Then x times z, huh? X times c, that will be 3x sine theta times 3 dx d theta. That will be integral from 0 to 2 pi 9 over 2 sine theta x squared from 0 to 5 something. And then let's do u substitution. u equals to 5 minus 3 cosine theta such that du is 3 sine theta d theta. And then if I change the limit of integration u at 0, that will be 2, right? And then u at 2 pi, it's also 2. I don't like it. Yeah, I don't like it because it suddenly kill each other. And 3 over 2 u squared du. Yeah, but this is equals to 0. I don't really believe this though, but apparently that's what happened, huh? Yeah, apparently that's what happened. Yeah, because the graph is symmetric with respect to the xz plane, right? I mean, sorry, xy plane. It's symmetric with respect to the xy plane, so it becomes an odd function for z. Okay, so, well, I have to believe it, I like it or not. So let's see S3. For S3, we have the plane x plus y equals to 5. So the factor normal to it will be 110. Right? And then the magnitude, therefore, square root of 2. So double integral over S3 of xz ds equals to double integral over that d1. You see the domain of the yellow one is actually the unit, the S1. Maybe I call it S1. Okay. The x then becomes 5 minus y z, okay, and then dA. If I make it polar, 0 to 2 pi, 0 to 3, 5z minus yc, that will also be 0, huh? You know what? Let me call this S1 first, dA. And then if I make it polar, that will be integral from 0 to 2 pi, integral from 0 to 3, 5 times r sine theta minus cosine theta sine theta r dr d theta. But this will become 0. Later on, this also becomes 0. Because the integral from 0 to 2 pi. Why everything 0? Okay, so the double integral over s of xc ds equals to 0 plus 0 plus 0. I don't like this, honestly. I don't think this is right. I don't think this is right. Oh, I missed something, but still it doesn't change anything though. I missed the square root of 2, the magnitude. From here, the magnitude. See the gradient of g, if this is the surface g, the gradient of g is 110. So the magnitude is square root of 2. That's the one I plug in here. Okay. Dude, I worked so hard for 0. You know. Yeah, but I didn't expect that though. This part here especially is the one that I didn't expect at all. I didn't expect this at all. Yeah, but I think the one that makes it a lot easier is the fact that it goes from 0 to 2 pi, and when I do substitution, substitution theta at 0 and theta at 2 pi, they are coterminal, then therefore they give us the same result. I'm sorry, but I feel like I have no confidence in the second question, number 12, is just tedious. But this one here, I think it's just too nice. The result is too nice that from an ugly number, from an ugly function, ugly shape. But that turns out to be nice. Okay, let's go on. This time we will work with the surface integral of a vector field, or we simply call this integral here the flux of F across surface S. Let me enlarge that a little bit. What happened? Okay, so we have this vector field F. That's C, Y, X. And the surface S is the helicoid in exercise 7. I copy paste that here. This is the helicoid here. Now let's remind ourselves. When we have double integral over S of F dot ds, now that ds is actually the F dot the normal factor, unit normal factor of that surface S. Okay, unit normal factor of that surface S. So, how to say that? So in this case, the N will be R sub U cross R sub V over magnitude of R sub U cross R sub V. However, the ds itself is the magnitude of R sub U cross R sub V dA, right? Okay, so this integral, after some substitution, will give us double integral over the domain of in U and V, okay, of the vector field dot R sub U cross R sub V dA. Okay, because these guys actually, when you multiply, they cancel. Okay, let's attack that plan. Let's execute that plan. So I think I will do what I need to do first is to find R sub U and R sub V and then the cross product. R sub U will be cosine phi, sine phi, 0. And R sub phi is negative U sine phi, U cosine phi, comma 1. So the cross product will be sine phi, negative cosine phi, U cosine squared phi plus U sine squared phi. Oh, that's simply U. So this is sine phi, negative cosine phi U. Okay, now using the same parameterization in terms of U and phi, then the C is phi, the Y will be U sine phi, and the X will be U cosine phi. Now put these things together, double integral over S of F dot ds is now becomes double integral over the domain D, which is 0 to 1 for the u by 0 to pi for the v. Okay, and then the f then becomes phi u sine phi u cosine phi dot, should we just do it outside for now? Yeah, dot sine phi negative cosine phi u, and then dA. That's double integral over d phi sine phi, and then minus u sine phi cosine phi, and then plus u squared cosine phi dA. Let's build it up then. That's integral from 0 to pi for the d phi, and then 0 to 1 for the du. This is u over 2 sine 2 phi plus u squared cosine phi. Okay, now you will see that this will go to 0. Notice that this integral is separable, right? Okay, imagine this, it becomes integral 0 to 1 of u over 2 du, and integral from 0 to phi of sine 2 phi d phi, you know. Okay, that becomes 0, right? Okay, and you will see this guy also becomes 0. This one is not though, that one is not. That will be simply integral from 0 to pi, integral from 0 to 1 of phi sine phi du d phi, integrate with respect to u will give us the length, which is 1. So we basically integrate this right now. Okay, and then from there we do integration by parts. So that is equals to negative phi cosine phi plus sine phi from 0 to pi. At pi, that would be negative pi cosine pi. So that's negative pi times negative 1 plus 0 minus, when phi equals to 0, that's 0 plus 0. So the answer is pi. Okay. Number 26. We have that vector field. Let me rewrite it first. Make it a bit larger. More space. So the vector field is xz, xy. The surface is hemisphere, x squared plus y squared plus c squared equals to 25, with y positive. So it is a hemisphere facing to the right. Okay, and the direction is positive y-axis. Okay, so how do we want to do this? Let's do the gradient. So let's call this gxyc here. Okay, that's a level surface, right? When we do the gradient, we will get the factor normal to the surface. Is it right? Now, then we want to make the y component, because you want a positive y-axis, it means you want the y component to be 1. Okay, so this is parallel to the factor that is 2, actually x over y, 1, c over y. Okay, that's the factor normal to the hemisphere. Now, is the length equals to 1? We don't know yet, but I think we can see that later on. What's the length? But I don't think that's the issue. I don't think that's the issue. Okay, so that's the normal factor. Not unit though. It's not unit normal. No, it's not. I don't want to use unit normal factor there. I was about to write this, but that's not correct. It's only parallel. This represent normal, which is true. This is normal to the surface, but it is but this notation also means it is unit, means the length is 1, which is not the case. Okay, and that's not the case. Well, but it's parameterized by x, y, z already. Okay, so the double integral over surface S of f dot ds is equal to, if I do the dot product, double integral over now d, so the d is now here, this on xz plane. Okay, this on xz plane with radius 5, right? That's our d. And then when we do the dot product, we get x squared c over y plus x plus z dA. But what is the y? I hope I don't make miscomputation somewhere. Divide by 2y, divide by 2y, divide by 2y. So when I do the dot product, this guy, that's right, this guy, this guy. So we get x squared c over square root of 25 minus x squared minus c squared for the first term, plus the x plus the c dA. Okay, now then because the domain is a circle with a disk with radius 5, then I will make it into polar, integral from 0 to 2 pi, integral from 0 to 5. This is r cubed cosine square theta sine theta. I make it like this, x c to be r cosine theta, and the c is r sine theta. I parameterize it that way. Okay, over square root of 25 minus r squared plus r cosine theta plus r sine theta r dr d theta. Now what I want you to see is that you will notice that this guy will go to 0. Okay, just split the integrations. Okay, and then you will see the second and the third term will integrate to 0. Now then the first integral becomes integral from 0 to 2 pi of cosine squared theta sine theta d theta times integral from 0 to 5 of r cubed over square root of 25 minus r squared r dr. Hold on, but the first integral gives us 0, huh? Don't you think so? Yeah, but since when you do substitution, u equals to cosine theta, right? Du is negative sine theta. I don't think that's the issue. But u at 0 is 1, but u at 2 pi also 1, huh? Okay, so this is 0 times something, which is 0. I hate this part. It's like we work so hard to get a 0. That's for number 26. Actually, I think I would also, I prefer to do it this way, to be honest with you. Okay, I prefer to do it this way, but because this is part of a sphere, hemisphere, then you may want to use the spherical parameterization, where in spherical parameterization, x, y, z is being parameterized by rho sine phi cosine theta, rho sine phi sine theta, and rho cosine phi. Okay, now in this case, the rho is 5, right? The rho equals to 5, and then the theta will be from 0 to pi, right? The theta is from 0 to pi, okay? And then the phi also from 0 to pi. Now, and if you remember, the r sub phi cross r sub theta, this should be the radius square, in this case 25 sine phi, and then sine phi cosine theta, sine phi sine theta, and then cosine phi. You try to work it out, but if you remember from my notes, that's what I have. Let me see if I have that note. Give me a second. I show you the notes then. This one here. This one. If you can memorize or at least put in on your scratch paper, your cheat sheet, that would be nice, right? But I think this worth remembering. Okay. Now, therefore, if I use that spherical integration, then it will be double integral. You know what? Let me do the f first. So the vector field f will then be the xc, the x times c, that's rho squared sine phi cosine theta, that's for xc. The x will be rho sine phi cosine theta, and then the y will be rho sine phi sine theta. Now then f dot r sub phi cross r sub theta, that will be there's a, a long one. Oh, I can change the row becomes 5. I can change the row becomes 5. So this is 25 here, 5, and then 5. Okay, so rows f dot, the cross product will be 25 sine phi, that's the common factor, times the factor this guy times this guy. That will be 25 sine squared phi cosine squared phi plus, are you sure you want to do it this way? Plus the second component, that's 5 sine squared phi cosine theta sine theta plus the third component, the dot product of the third component, we will have 5 sine phi cosine phi sine theta. I don't want to do this. We can factor the 5 out, so 125 and then 5 sine squared phi. I'm sorry, this should be theta, I believe. This should be theta here. Cosine phi cosine squared theta plus sine squared phi cosine theta cosine sine theta plus sine phi cosine phi sine theta. Now the thing is, when we do the integration later on, the theta will be from 0 to pi and the phi also from 0 to pi. Okay, 125 sine phi. So we have 125 sine phi blah 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 d phi d theta. Right, now you will see the following. When you integrate this respect to phi, this will be 0. When you integrate this respect to theta, it will be 0. Because this becomes 2 sine, I'm sorry, 1/2 sine 2 theta, right? When you integrate this, it will be 1/2 sine 2 phi, whose period is pi. So when you integrate respect to phi from 0 to pi, it will be 0. Okay, now here when you do substitution, you will get u cubed. So when u equals to sine phi, you will get u cubed, right? But then the limit of integration will be from 0 to 0, right? Maybe I write it u at 0, there will be 0, but u at pi also 0. Okay. In other words, when you integrate this ugly thing here, it will eventually become 0 anyway. Okay, I still prefer the first method. I still prefer the one I did in blue, because I basically take advantage of the fact that I can do the gradient, and then I get the gradient of g. Okay, and then because it is positively oriented, positive y-axis, so I make the y component positive 1. Okay, now then I do the dot product and integrate that from there, and this way I can maintain my domain to be that d here, the disk with radius 5. That's the one I like. Okay, let's go on. Number 30, the vector field F x, y, 5, and S is the boundary of the region enclosed by cylinder x plus c squared equals to 1, so it is parallel to the y-axis. The planes y equals to 0 and x plus y equals to 2. Oh, okay. So later on it becomes like this. It's slanted. This part here is slanted. Okay, let's talk about the surface first. So the one underneath here, on the left hand side, left wall, the bottom of that cylinder, call that S1. That's x squared plus c squared less than equals to 1, but the y equals to 0. Okay, And then S2, let's say that's the lateral region. That's a lateral region, including the one at the back. Okay, S2 is where x squared plus c squared equals to 1, but the y is between 0 to 0 to 2 minus x. Okay, we will parameterize that this way later on. Xz, we parameterize that using the radius is what? 1, huh? So it's a cosine theta, sine theta. So the y will be from 0 to 2 minus cosine theta. Now the third surface, call that this one here. The third surface is the slanted one. That's the surface where x squared plus c squared is less than or equals to 1, but the x plus y equals to 2. Okay, let's work it out. So double integral over the surface S, which is the enclosure of this ugly cylinder, okay, of f dot ds is now seen as double integral over S1 plus double integral over S2 plus double integral over S3 of f dot ds. Now over S1. For the first surface, the one in blue, okay, the y equals to 0, right? So the normal factor will be 0, 1, 0, right? In fact, that's a unit normal factor in the positive x-axis. But we don't. Do we have? Now they don't say the direction, huh? Oh, okay. So if they don't say the direction, we need to assume it is outward, and if it is outward, then it will be going out that way. That's the direction. I'm sorry. So the normal factor should be 0, negative 1, 0. That's what it's supposed to be. Okay. The region S1 is X and then Z here. Okay, that's S1. So I will parameterize that f dot ds is equal to double integral over still over S1, but the vector field becomes x 0 5 dot 0 negative 1 0 dA, but the dot product equals to 0. So this is 0. Okay, no big problem. See, if you set it up properly, you will see canceling things. But if you do things too fast, you don't realize that though. Okay, that's for S1. How about S2? For S2, this one is painful. Okay, so it will be double integral over S2 of f dot ds. That becomes over, let's call this D, the domain for S2. The f will be, the fx is cosine theta, y 5, and then the normal factor, oh, we use cylindrical there, huh? If we use cylindrical there, what will that be? That will be 0. Okay. the x component. That will be cosine theta 0 sine theta. dA for now. You may wonder about that parameterization, but let me show you that parameterization in our notes. When we use cylindrical parameterization, here the parameterization, it's a cylinder parallel to z-axis, right? But if we make it cylinder parallel to the parallel to the y-axis, then the y-axis will get the 0. Okay, and the radius 1, so the a equals to 1. Okay, so this will be integral. The theta will be from 0 to 2 pi. The y will be from 0 to 2 minus cosine theta. Okay, the dot product will be cosine squared theta plus 0 plus 5 sine theta. R, no R. This is just dy d theta, dy d theta. But it's independent of y. The integrand is independent of y, so I just multiply by the length right away. That's cosine squared theta plus 5 sine theta times 2 minus cosine theta d theta. Here we will get a bunch of 0 again. Well, because it's from 0 to 2 pi, right? But let's work it out. Let's work it out. Let me just steal some space. This is integral from 0 to 2 pi 2 cosine squared theta, and then minus cosine cubed theta plus 10 sine theta minus 5 sine theta cosine theta d theta. Because this guy here is basically 5 over 2 sine 2 theta, and when you integrate that with respect to on interval 0 to 2 pi, it will get killed. So this will become 0, this will become 0. Okay, now then the first integrand, the first term of the integrand will give us 1 plus cosine 2 theta, right? That's for the first integrand. And then the second integrand, the second term, I will make it 1 minus sine squared theta cosine theta d theta, like this. Why? Because then this becomes integral from 0 to 2 pi 1 plus cosine 2 theta, which will become 0, minus cosine theta, which will also become 0, plus sine squared theta cosine theta, which will also become 0. This will become 0 because the period of cosine 2 theta is pi. Okay, the period of cosine theta is 2 pi, and this has when you do substitution, u equals to sine theta, you will see u at 0 is 0, but u at 2 pi also 0. Okay, so we end up with this only, and therefore that will be just length of that interval 2 pi. That's for the second surface. The third surface, don't forget. The third surface, the factor normal to it is 1, 1, 0, right? That's the factor normal to it. The slanted one, okay? And then double integral over S3 of xy5 x, but the domain will be x and c, huh? So the while need to be written as 5 minus x, and then 5 dot 110 d a, and so I need to call this d3 now, the domain. Maybe I write it properly first. I write it properly first. So here's what happened. So in S3, we get x, y, 5, right? Dot d s, right? Which then becomes 110 ds without oriented notation, without the arrow. Okay, that will give us double integral over S3 of x plus y ds. Actually, this is over square root of 2. Now, ds itself is square root of 2 dA, domain of surface 3, x plus y becomes x plus 5 minus x, I'm sorry, 2 minus y, x. Okay, and over square root of 2, but the ds is square root of 2 dA. Now, but d3 is basically equals to s1, if you remember, which is the disk with radius 1, right? The disk with radius 1. To dA. So the area, this is twice the area of S1, which is pi. So the double integral over S of f dot ds in this situation, oriented S, is equals to 0 plus 2 pi plus 2 pi equals to 4 pi. Okay, that's a long work, huh? Let's continue. Number 40. Find the mass of a thin funnel in the shape of cone. So the cone is c equals to square root of x squared plus y squared, and the c is between 1 and 4. Huh. So it is actually a cone, right? C equals to r. Okay, but from c equals to 1 to c equals to 4. Okay, so the shape should be something looks like this. Yeah, but only this part, only this part. If the density rho is 10 minus z. Okay, so the mass equals to double integral over that surface times the density ds, is right? Okay. So density is easy. But the surface S, z equals to square root of x squared plus y squared. So z sub x equals to x over square root of x squared plus y squared. Right? It's supposed to be 1/2, but 2x here. Z sub y, similarly. So square root of 1 plus c sub x squared plus c sub y squared, that will be square root of 1 plus x squared over x squared plus y squared over x squared plus, oh, that's just a 2, huh? Square root of 2. Huh, okay. Now the shadow of this funnel here on the ground will give us, do you call that a donut? Right? A donut. From radius 1 to radius 2. Okay, so if we go back to that mass, that's double integral over s of 10 minus z ds. Okay, but the s now becomes d, so that the ds becomes square root of 2 dA, right? This guy becomes this, so that this can becomes this, which is the donut. Of course, the integrand, you need to change what that z equals to on that surface, which is 10 minus square root of x squared plus y squared, right? But then, let's take advantage of the shape. The shape is donut, so integral from 0 to 2 pi, integral from 1 to, oh, I think it's 1 to 4, huh? Yeah, 1 to 4, not to 2 though. It's up to 4. Up to 4. Right? Because the c here says 4, but c equals to r. So the radius is 1 to 4. And then we get 10 minus r square root of 2 r dr d theta. So that's square root of 2 times 2 pi integral from 1 to 4 of 10r minus r squared dr. That's 2 radical 2 pi 5r squared minus r cubed over 3 from 1 to 4. 2080 minus 64 over 3. 5 minus 1/3. So this is 2 radical 2 pi 75 minus 63 over 3. That's 21. 54. Is that right? 21 subtracted from 75. 54. That's 108 radical 2 pi. Yeah, you notice that we actually spend more time with the setup, huh? That's for number 40. Number 42. Honestly, I'm very tired. Let's do 1 or 2 more. Okay, number 42. Let S be part of the sphere that lies above the plane Z equals to 4. Oh, okay. So if we have the RZ coordinates, this is R squared, right? So then it becomes a circle there with radius 5, and you cut it at C equals to 4. So we are actually talking about this cap here. We are talking about this cap. The cap, this cap here. Oops. Let's c equals to 4. Oh, then if c equals to 4, the radius will be 3, huh? Right? On the ground. I mean, if we project that to the ground, then that will give us a disk with radius 3. Imagine it this way now. If you have that circle, I'm sorry, if you have that sphere. But we don't worry too much about the whole sphere. We only worry about that cap, right? The cap will have the shadow, a disk with radius 3 on the ground. That will give us the domain of integration though. Okay, so how about, we need to find the central mass. We need to find the mass first then. But the density, because the density is constant, so the mass will be the constant multiple of the volume. Oh no, the constant multiple of the area, because it's two-dimensional surface. So area of S. So the mass equals to K times double integral of ds. S ds. Which will be K times integral from 0 to 2 pi, integral from 0 to 3. How about the parameterization there? Does 2x, if g x y z is that surface x squared plus y squared plus c squared equals to 25, then the gradient of g is 2x 2y 2z, okay, which is normal to that surface S, right? And we want to make the c component to be 1. Okay, so I divide by 2z, I get x over c, y over z1. Now what is the length there? The magnitude of that will be square root of x squared over c squared plus y squared over c squared plus 1. That will give me, on the numerator, I will give me 25. The denominator give me c squared. So the square root will be 25 over c, which is square root of 25 minus x squared minus y squared. Okay, so then this will be 25 over, why 25? Yeah, 25, no, not 25, it's 5, duh. It's 5 over square root of 25 minus r squared r dr d theta. So that will be 2k pi, the k and the 2 pi, right? And then if I do u substitution, we do this too often such that I rather memorize that in future. That will be 25 here, 9, that's 16 here, 5 over square root of u, and r dr becomes 2, negative 2 r dr. It becomes du over negative 2. Cancel the 2, reverse the order of integration, the limits of integration. Okay, pull the 5 out. That's u to the power of negative 1/2 du. That is 2 times, so 10k pi u to the power of 1/2 also 10k pi. Okay, that's the mass. Since the density is constant and the shape as r radial, means if you rotate that radial with respect to c axis, then the x bar y bar must be equals to 0. Okay, but you need to you can say they are 0 without computation, but you need to give the reason, and the reason has to be both of them. Okay, the shape of the surface or whatever the domain of integration you have, okay, the shape of the item you are integrating, okay, and also the density has to also radial. Okay, now so we are now need to find the c bar, but c bar has the moment with respect to xy plane. We will do the same integration, but we insert c. Okay, we insert c. But the c is square root of 25 minus r squared. Okay, while the ds, as we saw earlier, that's 5r over square root of 25 minus r squared dr d theta, right? Let me show you. This guy, if you think about that, it becomes this. That's what we have, right? And this is our z. Therefore, now we have k times 2 pi times integral from 0 to 3 of 5r dr. Okay, that will be 10k pi r squared, so 0 r squared, 9 over 2. So that would be 45k pi. Therefore, the z bar will be 45k pi over 10k pi. That's 4.5. So the center of mass, the centroid in this case, because the mass, the density is constant, will be 0, 0, 4.5. Okay, that's the center of mass. That's for part A. Actually, part A should start from here. Part B, moment of inertia. Part B, moment of inertia is the moment with respect to xy plane. Actually, they say something. Moment of inertia about the c-axis. Oh, just about the c-axis. About the c-axis means double integral over the surface S. Okay, and then the distance from the c-axis will be x squared plus y squared. Okay, and then times density ds. Is it okay? But then this becomes integral from 0 to 2 pi, integral from 0 to 3, and then r squared k 5r over square root of 25 minus r squared dr d theta. That's basically it. Okay, I hope you can integrate this yourself, but let's do it anyway. U equals 25 minus r squared, so du equals to negative 2 are dr, and then u at 0 is 25, u at 3 is 16, and r squared is 25 minus u. So the integral now becomes 2k pi from 25 to 16. The r squared becomes 25 minus u. 5 over u, r dr becomes du over negative 2. Okay, cancel the 2 and reverse the limits of integration. I get k pi integral from 16 to 25. This is to the 1/2, by the way. Okay, and then I have, let me pull the 5 of 5 out. So I get 25 u to the power of negative 1/2 minus u to the power of 1/2. So that's 5k pi 50 u to the power of 1/2 minus 2/3 u to the power of 3/2 from 16 to 25. So 55 minus 4 minus 2/3, 125 minus 64. That's 5k pi 50 minus 2/3 times what? What is that? 36 plus 25. 36, 25, 61. Oh, okay. I don't like that though. So 5k pi over 3, 150 minus 121. Is it 122? Sorry. Which is 28, huh? Is it right? 28 times 5, 140 k pi over 3. I hope I don't make miscomputations anywhere, but the technique is there. The technique is there. Okay? Let me rest a little bit. I'm really tired, honestly. Okay, let's continue again. Seawater has this density and flows at a velocity field. So the velocity field is yx 0. Okay. And then find the rate of flow outward through hemisphere. So the surface that we are dealing with is x squared plus y squared plus c squared equals to 9. Let's c is positive. So it's a hemisphere with radius 3. Okay, so this actually the rate of flow, that will be double integral over density times velocity dot ds. Right? That's the rate of flow outward. Oh, we need to make it outward. So let's orientate that upward then. So suppose this is our G, the surface. Okay, augmented surface, then the gradient of G will be 2x, 2y, 2z, and then orientate that upward, that's parallel to x over c, y over c1. Okay, and then the floor, the domain is actually a disk with radius 3. So if this is the surface, then this is the D, right? The one in blue. Okay, therefore when I do the dot product, there will be rho y is x0 dot x over c, y over c comma 1. Actually, I need to change the c first because I don't want you to misunderstand the c as 0 in that case. Let me change this. This is x over square root of 9 minus x squared minus y squared, y over square root of 9 minus x squared minus y squared, comma 1. dA, and this is now d. That's rho integral, not rho anymore. That will be 2xy over square root of 9 minus x squared minus y squared dA. Oh, that's actually really nice. Because once I make it polar, integral from 0 to 2 pi, integral from 0 to 3, on the top I will get 2r squared cosine theta sine theta over square root of 9 minus r squared r dr d theta. The nice thing about this, oh, suddenly I light up because I can pull this 2 rho integral from 0 to 2 pi of cosine theta sine theta d theta integral from 0 to 3 of r cubed over square root of 9 minus r squared dr, and we know this is actually give us 0. Okay, that gives us 0. By the way, this is I didn't pay attention to this, but I need you to realize this is actually an improper integral because we have a pole. It becomes undefined when the r equals to 0. I mean the r equals to 3. Okay, so we're supposed to use limit when you integrate that. Just be careful. Just be careful. Okay, just be careful. You don't need to though, because in this case especially because we know this will be 0. Okay, thinking about what it actually looks like, the velocity vector field looks like this at 1, 0, 1, 0. It looks like this, huh? That's what the vector field look like. So given that you have a radial domain, right? Notice that the vector is actually always tangent to the level curve, right? Okay, which means that there's actually no outward flow. The water is actually just circling there. You know, it's just circling there. There's no water coming in or coming out from that through that surface. Okay, at least in total. Okay, I didn't expect that answer though. I have to be honest with you. I didn't expect that answer. But thinking about it again, why it looks like that? I think that's a reason. Okay, at least computationally, that's we get 0. We have too many zeros answered. You know. Okay, let's go on further. Last one. The temperature at a point in a ball with conductivity K. What is that? Oh, conductivity of the heat transfer thingy. Okay. So conductivity K is inversely proportional to the distance from the center of the ball. Okay, so suppose let the ball is centered at origin and then with radius A. Okay, so with radius A. So the ball has equation x squared plus y, has inequality x squared plus y squared plus c squared less than equals to a squared. Okay, and then the temperature at coordinate x, y, z is inversely proportional to the distance from the center of the ball. So this is the distance from the center of the ball. Okay, that's the temperature. We want to see the heat flow. So the gradient then, how the temperature actually flows will be C times the derivative of that respect to x will be negative x over square root of x squared plus, this is c times x squared plus y squared plus c squared to the power of negative 1/2. So it will give me negative 2 at the bottom and then 2x. Okay, yeah. And then I need to cube that, Right. I cube that because it's 3/2. Similarly, there will be negative y over square root of x squared plus y squared plus c squared being cubed. And then negative c over square root of x squared plus y squared plus c squared being cubed. Okay, let me factor the negative and factor that x squared plus y squared plus c squared to the power of 3/2, and then we get x, y, z here. Okay, and then find the rate of heat flow across the sphere. So the surface S is this, x squared plus y squared plus c squared equals to a squared. So the rate of heat across that will be double integral over this vector field, negative c over square root x squared plus y squared plus c squared to the power of 3/2 x, y, z dot ds. Okay. Now the thing is, this is a full ball, how do I parameterize it? Let me parameterize that using sphere. So I will parameterize this surface by r phi theta, a sine phi cosine theta, a sine phi sine theta, and then a cosine phi. As I remember, r sub phi cross r sub theta will then be, it will be a squared sine phi cosine theta sine phi sine theta, and then cosine phi. You know what? Hold on. Let me play this a little bit. Our xyc will be what then? This is our x, this is our y, this is our c. And if I multiply by a here, that will give me xyc. So a sine phi x y c. Okay, so this will become on the domain D already, where D is for the phi, it will be from 0 to pi, and then the theta will be from 0 to 2 pi. Okay, so this is C over, this is a to the power of 3, huh? That's a to the power of 3, but we have xyc. What I want to say is this. This guy times this guy will give us a sine phi x squared plus y squared plus z squared, which is a squared. Is it right? Hold on. So so everything cancels. Oh, a cube, the a's cancel, so we end up with double integral from 0 to 2 pi for the theta, 0 to phi for the d phi. We have negative c here. Is that right? Okay, so there will be negative c times 2 pi times integral. That's another 2. So that will be 4 c pi with negative. I wonder if my negative is supposed to be there. But I think so, huh? I think it's supposed to be negative because the further you are from the center, the lower the temperature, right? Okay, so we're supposed to have the heat coming. This means the heat coming in. Oh, hold on. I missed something. I missed the conductivity. Okay, so this is K here. This is K. This is K.